All right, let's get started. Hello, everyone. I'm Jinhua Zhao, Professor of Cities and Transportation at MIT. Welcome to the MIT Mobility Forum, designed by the MIT Mobility Initiative. Today, I'm really excited to have Professor Fred Mannering come join us, talk about highway safety, particularly the contemporary issues and the forthcoming age of autonomous vehicles. Right? Highway safety problems have really persisted. I would say even getting worse in recent years, right? Traffic fatality in the United States actually increased 10% from 2020 to 2021. Here, maybe I just show a quick chart to get some context here. So this is showing the total deaths, the green line, over the century here. It peaked around 1960s, going down until 2009, 10, etc. But then it goes up in the last few years. So we are actually not going to persist. We're actually going to the wrong direction, I would say. And this actually happened at the same time where we had all sorts of innovations, technology, policies, instruments try to reduce safety here, right? So this persistence, as Professor Mannering will argue, that is really because of the interaction between the safety intervention and the human behavior, the human responses to this improvement, right? Highway safety remained a perplexing problem that both engineers and also social scientists try to resolve, but yet to succeed in this. I would say there's no better person than Professor Fred Mannering who can really shed light on this puzzle. As he wrote in the abstract I shared with everyone, unfortunately, currently the safety-related application of, say, artificial intelligence and machine learning are making the same mistakes. These are likely to have disappointing safety consequences for the forthcoming years, where autonomous vehicle will be interacting with many of the human-driven vehicles for, I think, decades to come. But if these data analytic pitfalls of the past are recognized and avoided, then there is indeed a huge potential for AI and ML to vastly improve the safety, particularly in this forthcoming interactive regime of autonomous and human-driven vehicles, right? Before I formally introduce Professor Mannering, I do want to warm up the audience here by inviting everybody to type your organization, location, and time so that Professor Mannering know who the audience are. So I would say MIT, Cambridge, 12 now. Also, I try to reinforce the norm of this forum, which is I hope everybody to contribute an idea, right? Either as a question or a comment to Professor Mannering's presentation. Fred Mannering is alumni of MIT, graduated from PhD in 1983. He's a professor in the Department of Civil and Environmental Engineering at the University of South Florida, where he runs the Center for Urban Transportation Research. Before then, he was the head of the Department of Civil Engineering in Purdue University, also previously in University of Washington. His body of research has been cited over 37,000 times in Google Scholar. And he founded and currently the editor-in-chief of the journal Analytical Method in Accident Research, which really ranked the top one among transportation journals. And before that, he was also the editor-in-chief of Transportation Research Part B, Methodological. He received numerous awards and recognitions, including the Web of Science highly cited researchers for many, many years, the Council of University Transportation Center Lifetime Achievement Award in 2021, and the most cited also is the 50 years history of the Journal of Accident Analysis and Prevention, right? And also I want to mention the annual foundation top 10 transportation thought leaders in academia, right? Without further ado, let me pass the forum to Fred, please, right?
Good. So let me share my screen, get started. So today I'm going to talk about is perspectives of highway safety. And as was noted in the introduction, we have seen an increase in the number of highway deaths and pedestrian deaths. And I'm going to give some insight into what might be causing those increases. So let's look about, what has been happening in highway safety. We've had incredible advances in vehicle safety technologies, multiple airbags, autonomous braking, lane departure warning. I mean, just countless safety innovations. And we've also had drunk driving policies that have tried to affect some of the behavior. We've had texting laws, red light cameras, so many, many innovations. So with all of this, we would expect that highway fatalities and pedestrian fatalities on highways and bicyclists, vehicle interfaces, we would expect all of these to be declining. But they haven't declined. And this gives a little explanation of what's been happening. This is a shorter time period than was presented initially. But if we look at from 2011 to 2021, we can see it's like pretty flat, even though these incredible vehicle technologies are being implemented. And then, of course, we do have the spike in 2020 to 2021. And the fatalities in the blue include pedestrian and vehicle fatalities, any highway-related fatality. And then the dotted line is fatality per 100 million vehicle miles traveled. So it's not just, oh, there's more cars, we expect more fatalities. The rate is actually increasing. So let's look at what are some of the disturbing highway safety trends. One is that bicyclist fatalities have gone up 55% from their 2010 low. Motorcycle fatalities, again, these are like vulnerable road users, have reached all-time highs, including a 21% increase from 2019 to 2021. And pedestrian fatalities have increased 80% from their 2009 low. So what I'm going to argue is like, what's going on here? I'm going to point to four. I mean, there's many things going on. And obviously, it's a very complex engineering, human behavior interaction. But I'm going to look at four things and argue that we've not accounted for the effects of safety innovation on human behavior. We put in a technology, but we don't think about how people are going to respond to that technology behaviorally. We've not considered the externalities of the vehicle technologies that we've implemented, the vehicle safety technologies. We've not accounted for the evolution of human behavior. And I'm going to argue that human behavior is changing in fundamental ways, not just because of the safety innovations, although that's one reason, but there's just a natural evolution of attitudes and behavioral preferences. And then we've relied on flawed data analytics. I mean, we have many possible data analytic methods, but there are fundamental elements related to data analysis that we have not fully considered. So let's look at point one, the effects of safety innovation on driver behavior. So let's say we have the introduction of safety, and I will argue that the introduction of safety innovation changes behavior in fundamental and perhaps unexpected ways if you don't think about it. Let's consider an example of a technological innovation that improves safety. What will happen? So I have this little diagram from one of the papers that I've published on this subject that looks at the possibility of compensating behavior. So we have some initial conditions. On the horizontal axis, we have a selected normal driving speed, but it doesn't necessarily have to be just speed. You could drive distracted and things of that nature. And on the vertical axis, I have the probability of an injury accident. Now, each person has some equilibrium point A on the initial conditions curve here, where they have a car or whatever, and they like to have some probability of avoiding an injury accident. So they might have like, oh, when I drive, I like to have a 1 in 10,000 chance of being in an injury accident. Everyone will have a different point A depending on their risk profiles and so on. But let's put in the safety innovation, which moves the curve down from the initial conditions curve to the safety innovations curve. So the curve slips down, and we expect as engineers that people will keep driving the same speed and they'll move to point B. So the probability of an injury accident will decrease accordingly, and we'll move from point A to B. But really what happens is some people might say, well, you've made this car safer. I still like to have a 1 in 10,000 chance of having a crash. So I'm going to move from point A to C. That's complete compensating behavior. But realistically, some people are not going to be driving at the same speeds. They'll probably drive somewhere between B and C. So for example, at point D in the diagram here, where there's some compensating behavior, but there's still some net effect. Now, if there's complete compensating behavior, that doesn't mean the safety innovation doesn't have a benefit to society, because driving faster or driving more distracted still has a utility benefit to the driver. So there's still benefit to society. It's just not a safety benefit. And there's also the possibility that people overestimate the effectiveness of the safety feature and end up at some point E, where they drive faster and have a higher probability, but that's less likely. So if we ignore compensating behavior, and we have done this a lot in the profession, this leads to an overestimation of the safety innovation effectiveness and unexpected consequences, which should have been expected. So I would argue a lot of the reasons why we're not seeing the great benefits of the safety features in cars is that compensating behavior is one of the many factors that is mitigating the potential safety benefits of these vehicles. Then there's externalities that sort of relate to this. So if there's compensating behavior, one way to think about this, if there's compensating behavior going on, people are driving faster or more distracted because they feel their vehicles are safer. That's going to be an externality. They're making their utility maximizing decisions, but if they're driving faster, vulnerable road users, pedestrians, bicyclists, motorcyclists don't have that those injury prevention devices. So there's a much higher probability of them being involved in crashes. So as an example of externalities of compensating behavior, safety innovations often result in faster and more distracted drivers, and the consequences, as I mentioned, vulnerable road users and drivers without the advanced safety features, the multiple airbags and so on, are be exposed to increased risk of injuries. And if we look at the vulnerable road user increases in terms of fatalities and injuries, pedestrians, motorcyclists, bicyclists, much of this can be explained by this compensating behavior. Next is the evolution of human behavior. How people's values and behaviors change over time. Now, there's a lot of literature that explains that human behavior is continuously evolving. Economics, cognitive science, everybody knows that people's behavior is evolving. But these behavioral shifts can be accelerated due to technological innovations, changes in risk perception, changes in societal norms, and so on. So this, the fact that if you think about it, if you're estimating a statistical model, not only do your X's change, your explanatory variables change over time, but your betas change over time. It's how the effect of the explanatory variable on the decisions that you're considering. And there's ample evidence in the safety literature that shows that statistical model parameters change significantly over time. And if we ignore these temporal shifts, this is going to lead to erroneous inferences and predictions, and also a misinterpretation of how effective the safety innovations are going to be. The next one I'm going to talk about is flawed data analytics. So we've been using statistical and econometric methods. More recently, we have data-driven methods, machine learning, and so on. But there's fundamental elements that we've not fully considered. And if you're an econometrics person, these would be elements related to selectivity, endogeneity, and identification. And I'll give some examples in a second. But the above issues are systematic and are endemic to highway safety data. And the consequences of ignoring them or not giving them some consideration is we'll have biased safety predictions and we'll be unable to identify underlying causality. So let's give an identification example. Suppose you're looking at motorcycle safety and you estimate a statistical model and you find that if it's raining, you have a higher probability of injury severity. So there's two possible explanations to this result. One is that rain does increase the injury severity, the Newtonian physics involved, reduced coefficient of frictions, and so on. But the second one is that only the riskiest riders ride in the rain, and they'll have more severe crashes whether it's raining or not. So the effect of the rain variable could be pure selectivity, and the actual rain itself has minimal effect. We've been, as analysts in safety data, we have been unable to untangle these elements. We are not sure how to, what is the actual effect of rain and what is the actual effect of the selectivity that might be caused by rain. And the consequences of that is you could come up with fundamentally different policies. So for example, if you thought it was the Newtonian physics explanation, it's like, well, we should have motorcycle tires with higher friction. But if you think it's the selectivity element, you should develop an advertising campaign that discourages motorcyclists from riding in adverse conditions. The next one, and this is an example that I actually wrote a paper on, is the effectiveness of vehicle safety features. And I wrote a paper on this in the early 2000s that looked at the effect of side impact airbags. So if you look at the development implementation of side impact airbags in vehicles, they're found to reduce fatalities relative to vehicles without them. But side impact airbags seem to become less effective over time. So what's going on here? One explanation is there's a self-selectivity. The people that buy the cars with most safety features are a self-selected group of the safest drivers. This is why any safety innovation that we develop with cars, if you look at the vehicles with the safety features and vehicles without the safety features, initially you're going to find that they're much safer than they appear because the safest drivers buy these cars. There's an inherent self-selectivity going on. And if we look at the side impact airbag effectiveness, the Insurance Institute for Highway Safety reported them 45% effective in reducing fatalities and side impact crashes. Then in 2006, it's 37, 2008, 31, 2010, 25. What's going on here is most likely the initial 2004, the safest drivers are owning these cars are going to be in situations that are less safety critical. By 2010, you're starting to get the real effect. And eventually, when you do like 2020, which almost all of the new cars have side impact airbags, you get a much better interpretation of the actual effectiveness of side impact airbag. So the thing to be cautious here, when you hear a new safety feature that, oh, this is 90% effective, we should do this, think about the fundamental self-selectivity. They probably, when you get those numbers, the most common thing is you look at the vehicles with the safety features and without, and that's exactly what you don't want to do because of the self-selectivity. You're always going to overestimate the effectiveness. So the future of highway safety in the autonomous human-driven vehicle environment. Now we can think about, we're putting autonomous vehicles into the vehicle fleet now, and this is going to create all sorts of things that we have to think about in advance. So what we really need to consider are the things, the elements that I've talked about: selectivity, temporally shifting behavior, compensating behavior, and the resulting externalities. So if we look at future possibilities, one way, as an example, to minimize the compensating behavior is to develop something like you might call an AI-assisted driving. And what this does is it adjusts vehicle safety systems after learning driver responses to changing conditions. And you can imagine that you could develop an AI system in a car that adjusts the safety features to mitigate risk compensating behavior. One way to think about this is you would make the car seem more dangerous than it actually is. So for example, if you have a really good braking system, you probably apply your brakes much later and have roughly the same probability of getting into an accident. But you could develop an intelligent system within the car so that it detects when you're applying your brakes and then thus mitigating potential risk compensating behavior. When we think of autonomous vehicles, and this is something that's really important as we start to introduce autonomous vehicles into the traffic stream. The current approach is we design autonomous vehicles to avoid collisions in response to human-driven vehicle trajectories. But I would argue that one of the most important things that we have to think about in autonomous vehicles is how they affect the behavior of human-driven vehicles around them. And I would argue the second, the alternative approach, is we want to design autonomous vehicles to interact with human vehicles to alter crash-critical vehicle trajectories before they happen. So for example, you could develop an autonomous vehicle that detects vehicle, close following distance behind it, flashes brake lights, does all sorts of interaction, maybe maneuvers, accelerates, decelerates, to affect the behavior of the human drivers around the autonomous vehicle. And the likely consequence, if we ignore the human response to autonomous vehicles, what we're going to find, and this is what we're doing now, right? We're just throwing the autonomous vehicles in and see what happens. What's going to happen is human driving behavior will change around the predictable driving of autonomous vehicles. And there's already anecdotal stories where an autonomous vehicle behaves in a very predictable manner. So drivers tailgate autonomous vehicles, cut in front of autonomous vehicles. But unfortunately, those behaviors they develop around these predictable behavior of an autonomous vehicle will propagate to their behavior around other human vehicles. So changes in behavior around autonomous vehicles will create unsafe behavior around human-driven vehicles, increasing the human-to-human driven vehicle crash rates. Now, this is most certain, this is my great prediction here. This is certainly going to happen unless we develop autonomous vehicles that can mitigate this. Because we were talking at the beginning where one of the arguments is that driver behavior during COVID is now propagating to the post-COVID years. So the bad habits we may have developed during COVID, when traffic volumes were low, police enforcement was low, there's probably some propagation of that. This sort of propagation will also happen with driving around autonomous vehicles and then human vehicles. So the future of highway safety, the fundamentals of human behavior are still not being fully addressed. When we develop a new technology, we're just expecting that it'll be effective based on primarily the engineering aspects of it. We're not considering the possibility of, for example, of compensating behaviors that people may start driving faster, more distracted, more recklessly to mitigate, perhaps totally, the effectiveness of these features. Now, there's some safety features such as shoulder belts that you can argue that we've not been able to compensate to overcome their true effectiveness. But the safety features that we've developed since those initial highly effective safety features of occupant restraint are not quite as obvious and not quite as powerful as that. So the compensating element can easily mitigate what the potential increase in safety is. Now, there's a lot of AI ML that opens up new possibilities in data analytics, but unfortunately, the AI ML, perhaps even worse than the statistics and econometrics, the people that are applying AI ML to safety data are not considering the fundamentals of human behavior, concepts of selectivity, endogeneity, changing behavior. All of those things are not being fully considered. So the current approach, as I mentioned previously, is we introduce a technology and we simply hope that the technology advances overwhelm the mitigating human behavior. And I should mention as I conclude here and we get into the exciting part with questions and interaction, I've written several papers with my colleagues on concepts presented in this talk. So feel free to look some of those up and you get a very detailed statistical and econometric analysis of what's going on with these data. And I think I'm not sure how, we're close to 20 minutes. So
Great. Thank you so much, Brad. You opened so much discussion points here, right? So we'll
Right.
jump into directly. One is toward the end, you mentioned this the aggressiveness of human vis-a-vis AV may propagate into a human-to-human interaction context here, right? So
Right.
I actually have an example. Last year I went to karting with my son, and right after when I drive home, I indeed find I actually drive much more aggressively. I couldn't help control myself. Actually, that's first time I had first ever accident I ever had on this, right? But then
Wow.
back to the AV discussion. So does that mean that we shouldn't design AV to be too conservative? So meaning building some degree of aggressiveness, like a similar on par with the human, may be better for the system perspective.
Right. Right. And first of all, to get to your compensating example, I should tell you, I think
It's already done. It's already done and gone.
was
Right, don't worry about it. Go ahead. Yeah.
Okay. So I should tell you that I own like 8 cars, and they go from the 1960, because I collect some, it's 1960, 1970, all the way up to 2020. Now, I should tell you that my newer cars have the full level 1, with the collision avoidance, the autonomous braking, adaptive cruise control. And to your point, when you notice how your driving behavior changes, since, when I start driving one of my level 1 cars, my behavior changes quite a bit, because now I know the car's safer. I start messing with my Apple CarPlay and all of this distracted stuff. When I get into one of my, 1960, 1970 cars, your life is in danger. And it becomes much more obvious. They don't brake as well. So, but we do have to be careful, because this is also a case where we have self-selectivity. If you look at the effectiveness of level 1 safety innovations, you find they're pretty successful, but you only observe the safest drivers driving these cars. I mean, if you actually, as my little anecdotal if you actually have these cars, you have an L1 car and a way non-L1 car. My 1960s car was like the first year with the shoulder belts, and no safety features whatsoever. It's like it was a survival of the fittest, right? But so that it's clear that compensating behavior has gone on. But to your point, it's not the way we design autonomous vehicles. We don't want them to design them so they have a higher risk of accidents, but there are ways we can keep it same very low accident risk, but still communicate to the surrounding human drivers that this car can still behave erratically while not actually increasing the probability of a crash. So for an example, if an autonomous vehicle is being tailgated, the algorithm just starts flashing the brake lights, sort of an indication that, and you don't even actually have to apply the brakes, right? You can just communicate with the drivers around it. So that I think is going to be a critical safety element of
That's
putting
interesting. That relate to the statement you made that make the situation seemingly more dangerous.
Right, exactly.
That's so interesting, both in terms of your own vehicle, but also signal to the other vehicles about this, right? Yeah. So here, then you mentioned 4 reasons that we may make mistake. The first one is a compensating behavior, right? For that, assume that the degree of a compensation will vary, either by different technology or by different group of people. Can we give some example where certain technology, somehow people compensated a lot, while certain technology people don't compensate much? What drives these different degrees?
Yeah, I think the areas where they compensate the most are the ones that you would consider active safety features. So for example, a passive safety feature would be like an airbag. Yeah, it's there and you might do some compensation, but an active safety feature that might be the autonomous vehicle braking or lane departure warning, that is something that I think you have a lot of compensating behavior. And to give an example, some of my, and again, anecdotal, some of my level 1 cars have heads-up display. So you just start focusing on that heads-up display that has the little radar indicators that tell you if there's cars beside you and stuff. And I realized you just don't look in your side view mirrors that much anymore because everything is in the heads-up display.
Yeah.
But when you go back and use your non-level one, non-heads-up display vehicle, it's very dangerous. There's an adaptation period. So I think the active safety features, the ones that are providing feedback, another example would be if you have a vehicle that has really good braking performance, almost invariably you'll start applying your brakes later and sort of mitigating some of the effectiveness of the braking system. So the active safety features almost certainly have compensating behavior, whereas the passive ones may have less so.
I see. So then to your second point about the externality, right? If at the individual level, you could argue that people just have a different degree of tolerance. So it's my decision to choose where do I balance between the two. But the thing is, if you choose a high risk balance, you also impose externality for other user who didn't choose to do so, right?
That's right.
Problematic. So for that, like see in congestion part, when we have congestionality, we have the device like congestion pricing, try to address that, right? Even though political difficult, but we somehow successfully implement some of that. In terms of safety externality, what are the meaningful policy interventions that we can internalize this externality?
Now that's an interesting point, and I'd have to think about that. I've been thinking that the most obvious solution to that sort of compensating behavior would be to develop a safety system in the car that mitigated the risk compensating behavior. I'm not sure if there's actually a policy that you could develop that sort of, and again, instead of there's a whole field of transportation safety that instead of looking at observed crashes, that looks at vehicle trajectories and near misses, right? So that might be, I'll give you an example of a study that I did in is sort of a real-time adjustment. We did video analytics of an intersection where we look at near misses. And if we start getting a high number of near misses, then we change the signal timing gets changed to avoid these, so you don't have to wait for a crash to occur. These things can be adapted in real time. But I think in this case, perhaps unlike congestion, it's hard. I mean, we've made over the years many safety related policies, but I don't see an obvious policy to mitigate this compensating behavior because it goes on and a lot of people don't even realize what they're doing. Right. So there's an awareness. It's not like for drunk driving, you have to quit drinking, but for how do you you're risk mitigating. I guess you could develop a system in the car that is determines when you're applying your brakes and gives you a warning, late brake application or something. Right. But it looks like instead of a sort of it has to be a policy that is centered around the specific technology.
Right. Oh, thank you. Yeah. So the third one about the temporally changing nature of human behavior here, right? Particularly, you mentioned that some of the behavior changes due to the safety technology itself, but some of the human behavior evolution are totally exogenous, is outside reasons, actually, right? Can you give us some example of that, and also what are the causes for such evolution?
So, as an example, that one mention, we say, well, that behavior changes in response to technology, but there's a very large body of literature that has determined that behavior changes because of macroeconomic conditions. And you may notice during the Great Recession in the late 2000s, there was a significant reduction in the number of crashes. And historically, what we have found, if you look at the aggregate data during recessions, there are fewer fatalities per mile driven. And during good economic times, there are many fatalities per mile driven. So if you're looking about how's our current economy is doing great because we have a lot of fatalities, right? Maybe that's so, but really the people that have looked theoretically at what's going on here is there's a lot of history that macroeconomic conditions change in fundamental ways people's risk profiles. And again, there's a whole body of research that sort of look at how this affects. Another element that inherently makes human behavior unstable is there's a difference between attitudes and behavior. So, we have an attitude that, oh, I would love to save the planet. And so, but then we have the behavior is I drive an SUV that gets 15 miles to the gallon. So how do you reconcile those two? And I think as we go through life, there's always a difference between our attitudes and our behavior. And there's a cognitive dissonance there, sort of the Leon Festinger thing from the early 60s. And we're constantly reconciling that dissonance, and that constant reconciliation of the dissonance between your attitudes and your behavior inherently make your behavior sort of unstable. So you're adjusting your attitudes and then you're adjusting your behavior. So there's a lot going on. And if you look at the fields of economics, I mean, there's work of Koopmans in the 1960s. There have been many people have looked at fundamental ways why people's tastes and behavior are changing over time. But it's there's many causes of that.
Thank you. Yeah. So probably the last question from me. So I encourage the audience again, put your comments or question to it. Then I'll give it to John to moderate that. So last question is more on the analytical part, right? Fred, you contribute to actually significant to both the kind of a classic statistics, econometric-based methodology, as well as the kind of recent machine learning-based methodology. Give a sense of how do they compare, particularly in the sense of falling into the victim of the four problems just usually illustrated.
Sure. So when we think of, I think a lot of people that use the data-driven methods, the machine learning, their primary focus is on prediction. Okay, but in addition to prediction, there's causality, because a lot of times just being able to predict something is usually short term and doesn't give you any insight into what is going on. So when you think of traditional statistics and econometrics, there's certainly a prediction element, but there's also a search for the underlying causality. So, and that, because it's the causality that will determine what an effective policy might be. And I think that's one of the major problems with the application of machine learning in safety data is that we're just focused on prediction. I mean, for example, in the journal that I edit, I get many papers that say, oh, look, this model predicts better than the econometrics model. Of course it predicts better, but we want to know not only prediction, we need to know causality, because it's the causality that is going to determine the policy that actually affects, that actually affects in this case, the probability of fatality or whatever we're looking at in the safety area. So that's the fundamental difference between the two, and both have advantage. I mean, there's an advantage. If you focus totally on causality, your prediction may not be so good, right? If you focus totally on prediction, you don't know what's going on. So there's a balance between those two that we have not yet struck in the field.
Right. A recent talk I just watched, you categorize this application into three buckets, right? The first bucket is this obvious area that AI will be just beautifully applied and nothing wrong, just go with it. The second category is AI with at least a moderate level of caution on this. And the third category is AI with extreme caution that you should apply on this. Give some sense about the three categories, people.
Right. So I mean, there are some applications that have to be real-time applications. You don't have time to think about the causality. You're collecting data and instantly providing a prediction. In that case, you're not so much interested in the causality because it's like an instantaneous react. So that's an obvious application of machine learning, right? Because it can do the prediction instantaneously. But when you get to a longer term and think about how it might affect in the future, then you really have to think about the causal effects.
Great, thank you. So now let me give the form to John for the audience Q&A. Yes,
okay, super. Thanks so much, Fred. Just before we kick off with the questions from the audience, I wonder if, one of the main points that you made was about the introduction of safety technology actually sort of changing people's behavior and causing them to embrace riskier behavior. And just for those of us who don't read, econometrics today at night, if you were explaining this to a smart 14-year-old, how would you explain your evidence for that? I think it was great that you articulated the difference between active safety features on vehicles and passive safety. But I think it's worth just returning to that, that if you could explain that a little bit more. What's your evidence?
Yeah, I would, instead of getting into all of the econometrics that actually uncovers that evidence, if I was explaining it to the way I would explain it to one of my children or something, although now both of my children have PhDs, so they can understand the econometrics. But if I was explaining it to them when they were younger, I think using the anecdotal explanation is perhaps the best. For example, in my case, when I'm driving my level 1 autonomous vehicle car, you can notice that I'm noticeably less attentive to the roadway than I am driving one of my 1970s cars. And there's a lot of, some of it, we've developed these safety features, but we also have things like Apple CarPlay, so we have all these safety features, but we have all these additional distractions. I remember one of my 1960s car, this was an MG, if any of you, remember the English car makers, but they were so concerned about distraction that the owner would not provide a radio as standard equipment. They thought the radio was too distractive to driving. But if we look at cars today, just think of what we have beyond the radio. I mean, you have all the, some of it is voice activated, but I can tell you, my Apple CarPlay, to try to play Amazon Music, I'm trying to have it play one of my band CDs or something. It's, I'm continuously distracted. So in some sense, we've, with all the advanced safety features we've had, we've also added a lot more distractions within the vehicle. And
Right.
the people have a greater opportunity to risk compensate from the distraction perspective, because now, and that is an important thing that we really haven't considered, because we develop the safety in one path, and you develop the amenities, Apple CarPlay in another path. We're not thinking about how those two interact.
Yeah, and that, in fact, I'm glad you raised distraction, because that's exactly what I was driving at, was if it's even possible to separate these two effects, the effect of increasing safety technology features, which, as you argue, is driving, in fact, riskier behavior on the one hand, and then, distraction, which of course has been a major focus of, road safety agencies around the world for some time now, and just how to disaggregate those two.
And, I should mention that even though my diagram had speed on the horizontal axis, it's really speed/distraction, right? Because I find when I drive my level 1 cars, they're not as fast as my non-level 1 cars. So I don't drive them faster, but I do drive them a lot more distracted.
Okay, I want to come to some of the comments in the chat, really interesting. And I think one of the, if not one of the first questions we had was from Bern Grush. And he basically said, have we accounted for increasing vehicle size and weight? Now, couple this with a question from Ben Pear, and why are collisions decreasing in Europe? So this is a related set of questions. I mean, one of our senior researchers, one of our senior fellows at MIT, David Zipper, has been writing a lot about car bloat and, vehicles just getting larger and larger and with higher surfaces, the greater heights at the front end of the vehicles, resulting in greater risk and indeed fatalities to pedestrians. First, what are your thoughts on car bloat? And then if that is a specific to the US conversation, please elaborate on that.
Yeah, I think the car bloat is a very serious issue. And, one of the, to give an example, with electric vehicles tend to be much heavier. Now, I should give you a little anecdotal story, is that just earlier this week, I bought a 1976 Triumph TR6, which is like 2,500-pound little British sports car, right? But the car that was on the trailer that was backed out before it was some BMW i6 or something. But I looked at the weight of that car is like over 6,000 pounds. And the weight of my little Roadster is like 2,500 pounds, right? So a lot of this, I think, with the car bloat, we are seeing perhaps a greater variance in the weight distribution on cars on the road, perhaps more than at any time in the history of the vehicle mix. Because now we have cars from like 2,500 pounds up to 6,000 pounds and over. These are just regular cars, not including heavy trucks and so on. So that weight distribution, I think, imposes an externality. People with heavy cars are imposing an externality on vehicles with lighter cars. Now, it's not just weight, because you have crumple zones and everything. You can have a car that is lighter and still be pretty safe if you have very innovative crumple zones and so on. But the car weight is, again, I think, one of the reasons. And as you mentioned, it seemed like in the 1990s, we were designing cars to be highly efficient from an air perspective, right? Coefficient of drag was very good. And the consequences of having good coefficient of drag is you have a nice slope on the hood. It probably was safer for pedestrians as well. But since then, we've become less concerned about coefficient of drag. We have more efficient engines and so on. And as you pointed out, a lot of the larger vehicles have these vertical grills. And, when you think of the injury in even small, low kilometer per hour collisions, it can be pretty significant. Now, with regard to Europe, it's interesting that, and almost all of the developed countries, aside, except for the United States, have noticed significant improvements over time in fatalities per kilometer driven or whatever. And I think, I'm not sure if it's a uniquely American phenomenon, what makes maybe people in the US more likely to risk compensate. That would be, again, I haven't followed the literature comparing, the behavior of US drivers versus European drivers. But, there's also an adaptation that goes on. I'm going to give you an example. When you drive in Boston, how people drive in Boston is much different than how they might drive in Tampa, for example. And so you can see disparities, spatial disparities within the US. And this got me to the point, let's say you had an autonomous vehicle that is actually learning from the vehicles around it, which, you have to be really cautious, having it learn driving behaviors from vehicles around it. But if you have an AI autonomous vehicle that was trained in Boston, and then you started driving it in Indianapolis or something, God knows, probably the first 100 miles, you'd have like 3 wrecks or something. So and I think when we think of the US compared to other developed countries, there's fundamental change, there's fundamental differences, I think, in behavior. And that tends to be reflected in how effective the safety features are from one country to the next.
Yeah, exactly. I mean, it is interesting that your risk profile of driving on a road in the United States is roughly twice that of driving on a road in Canada, when, there's not a huge amount of difference in the sort of characteristics of the two countries from a
I think there's some cultural fundamental cultural element that's going on. But yes, and this is, I think safety researchers in the US have been perplexed by this, because when they look at the the advances in safety that have been made in the European Union, and then compare that to what's going on in the US, it's a perplexing problem.
Yeah, actually, we have Peter Norton had posed a question that I want to come to, and maybe Peter, if you're still on with us, you can jump in directly. But before we get to that, I want to pose a question that Jane Chu offered in the chat, and she basically said, do these flaws mean physical interventions, for example, traffic calming, support public safety more successfully than safety features in individual vehicles? How do we achieve safe designs in the US transportation network, given not just flaws in individual thinking, but what Roger Ruddick has called an institutional flaw with how we educate our transportation engineers? I thought this was a very good question, and it was in the back of my mind as well, and I'm sure many of our viewers, about the question of how we actually design our road network. How do you think about that impact on safety?
Yes, I think because we can think about how the spectrum is going. At some point, maybe 60 years from now, we'll have all autonomous vehicles, and then the problem will resolve itself. Then it just becomes a software problem. But until then, I believe you're probably correct, and I'll have to make sure I do another edition of my textbook, Principles of Highway Engineering and Traffic Analysis. But when you think of what could be the most effective safety policy, it's probably not looking at controlling the individual behavior in specific vehicles, although artificial intelligence assisted driving, once we get safety features enough, we can start looking at those risk compensating elements. But as pointed out in the question, I do think probably before we get to that level, things like traffic calming and stuff are probably the best ways to address safety in the very short term. Now, it's interesting that there is a demand for safety features in vehicles, right? Because certain people want to be safe, and they tend to pay significant amounts of money for additional safety features. And the market is responding to that, right? So they're by level 1 automation. So there will be people that are seeking those safety features. But I think if you want to make a more, to the point raised, if you want to make an immediate impact, things about designing safer roads is probably more effective than adding more safety features to cars, unless you add the safety features and then develop the AI to adjust for the compensating behavior. Then you might be on the same playing field. But yes, I think we probably always overestimate the effectiveness of technology, right? So we're saying, oh yeah, we'll put this safety feature in, it decreases crashes. And as I mentioned before, these safety features are often justified. Oh, it is a 30% decrease in the probability of a crash. That number comes from the safest drivers, because those are the ones in those cars, right? It's really not 30%. And so we have to think about that self-selectivity when we get into looking at individual safety features. But yes, I think designing safer roads is probably the best way to go. But there's a cost to that too, right? Roads aren't cheap.
Yeah, well, absolutely. But I think the core of Jane's question is around this concept that, we have trained transportation engineers for generations at MIT and other institutions to focus on this concept of level of service. And level of service is a concept that just says you want to move more cars more quickly through the road network.
Mm-hmm.
And so it's interesting that that's the objective, rather than protecting people's lives. And
Yeah.
I think that's a little bit of where, at least in my mind, it creates this cognitive dissonance, and we need to sort of maybe rethink what the larger objectives are. Do you have thoughts on that?
Yeah, and when we design roads, it's not all for a level of service. A lot of it is the actual sight distance. There's a lot of accident prevention in there, stopping sight distance. So for example, again, this is like, chapters in my text on this, chapter 3, is we design roads for an anticipated eye height, expected stopping distance of the vehicle. So it's not just number of lanes, right? There is a significant safety element being considered in design of highway. But we design a road with, so for example, interstates are designed for 70-mile-an-hour driving speeds, but that's based on a standard vehicle with specified braking characteristics. If you have a high-performance car, you could probably drive that road with the same level of risk, maybe 80 or 90 miles an hour, right? But for the standard design vehicle, we design them for a certain speed to allow the vehicle to stop in a safe distance. So we do consider that, but as you can imagine, as was pointed out earlier, there's an incredible variance in vehicles on the road, right? You have this heavy trucks. It's interesting, heavy trucks that have terrible braking performance are not really the design vehicle because the driver's eye height is so high. And when you do vertical and horizontal alignment of design, that's much more effective than minimizing the braking distance. So we do consider elements of road design, but the high variance makes that a challenge. The high variance in the vehicles that drive on the roads makes it a serious challenge. So there's only so much we can do in designing the Newtonian physics of avoiding crashes, right? And when we look at it though, most crashes are caused by human error, right? And that's the great promise of autonomous vehicles. We get the humans out of the decision-making process, then it becomes much easier. If I give this talk 50 years from now, it's like, well, we did it. We have the machine learning and the autonomous vehicles. But to the point is a lot of people try to correlate traffic congestion with safety. And some people say, well, if you have high congestion, it's inherently safer because you can't get to the speeds that cause fatalities, right? So there's an interesting interaction between level of service and safety. But a lot of it, there's a lot of elements involved, like the speed variance in the vehicles. There's a lot of things that have to be considered there.
Excellent. We could go on. There's so many great comments that we will share with you in the chat, but we're out of time, so I'm going to turn it back to Jinhua.
Great, thank you, John. Thank you so much, Fred. This is really a brilliant discussion here. Most people, we see you as the brilliant researcher, but I do want to let people know that you also have two other very important endeavor. The first one I'm sharing is Fred is actually lead guitarist of a band, Vulgaris, and also as a motor racer here. So I would say you're probably the most colorful transportation professor in the world with all these different variety of interests and hobbies. So everyone, please join me. Thank Professor Fred Matterman for the presentation today.
Yeah, thank you. Thanks.